Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Mr. Manideep Gupta, Assistant Professor from Department of Aeronautical Engineering, MLR Institute of Technology. Today, the topic which we are going to discuss is electric rockets. Till this, in the previous lectures, we have gone through the combustion process, everything about the chemical combustion systems, like one propellant, one oxidizer, both has to react each other. After that, energy releases in the chamber that will lead to the pressure buildup and thrust develops. So, the concept of pressure buildup is by reacting the two substances, one is fuel and oxidizer. So the chemical reaction takes place between the fuel and oxidizer. So that's why that is called chemical propulsion system. Now chemical rocket, those are chemical rockets. Now we are going to discuss about the electrical rockets, right? So the today lecture is about electrical rockets. So how we are using the electrical energy to develop the thrust, that is going to be discussed in this lecture. Coming to the overview of today's presentation, we have introduction to electrical and magnetic fields which will help in generating the thrust, like electrothermal and arc jet thrusters. In electrothermal thrusters, we discuss arc jet thrusters. Next, we will discuss about electrostatic thrusters. Next, electromagnetic thrusters. These are the topics to be covered in this lecture series. Coming to the introduction to electrical and magnetic fields. You might have gone through this introduction about electrical and magnetic field in school days, but it is necessary to revise these topics once again for brush up. Introduction to electrical and magnetic field. So the way how the gravitational field exists and the gravitational force exists between two masses in this universe. Okay, if you take any two charged particles like a Q1 and Q2, and there is a distance between R, between the two charged particles, there will be some electrostatic force between these two charged particles. That electrostatic force F is directly proportional to the charge of the two charged particles, like a multiplication of two charged particles Q1 and Q2, and it is inversely proportional to the square of the distance between the two charged particles. Okay, right. Here the charge Q1 here the charge Q2, and this is the distance between the two charged particles R, and this is the electrostatic force develops, that is equal to F is equal to Q1 Q2 divided by R square. It's the same way like a gravitational force. Okay, coming to the Coulomb. Who gave this? Coulomb gave the law of such forces in a uniform similar Newton's law for gravitation. So Coulomb given a law of attraction between the two charged particles, like Newton gave law of gravitation. Okay, what is that for law is the force F between any pair of point charges is directly proportional to the product of the charges, that is Q1 and Q2, Q1 into Q2, and inversely proportional to the square of the distance R separating them. So inversely proportional to the square of distance R separating them. So this is the law given by the Coulomb to calculate the electrostatic force between the two charged particles, right? F is equal to K into Q1 Q2 by R cube into R bar. It is a directional, it is a vector. So Q1 and Q2 are the charges measured in the Coulomb, and this K is a constant. It is 9 into 10 to the power of 9 Newton meter square per Coulomb square. Newton meter square per Coulomb square. This is about the electrostatic force generating between the two charged particles. And this K can be written as 1 by 4 pi epsilon naught. K can be written as 1 by 4 pi epsilon naught. Here epsilon naught is the electrical permittivity of free space. Epsilon is a very important parameter to find the electrostatic force between the charged particles, right? So this epsilon naught is the electrical permittivity of free space. What is electrical permittivity? So this electrical permittivity is nothing but ability to store the charge in a medium. It is nothing but ability to store a charge in a medium. Suppose if there is some medium or some substance is there, it can store some charge. So how much extent this substance can store the charge? That is nothing but the ability of this substance to store the charge Q. That is nothing but explained by electrical permittivity. So here the electrical permittivity epsilon naught is the electrical permittivity of free space. So this epsilon electrical permittivity changes from one medium to another medium, one substance to another substance. Okay. The permittivity of any medium is given as epsilon. Epsilon naught is a free space, permittivity of free space. Epsilon is the permittivity of a medium. So here epsilon r is one more parameter which is called as relative permittivity. Okay, there is a relation between permittivity of a medium, permittivity of free space and relative permittivity. That is, permittivity of any medium can be given as epsilon is equal to epsilon r into epsilon naught. It is a product of relative permittivity and permittivity of free space. There is some medium I have. If I want to calculate the permittivity of this medium, I have to multiply the relative permittivity of that ER, and also I have to multiply with this ER with the permittivity of free space epsilon naught. This permittivity of free space, this is constant. This is constant actually. Okay, based on this relative permittivity, we can estimate the permittivity of any medium, so that we can find the ability of that particular material to store the charge in it. Okay, so this is about the permittivity of a medium. Next, electrical field. So it is nothing but the region around a charged particle can be defined to have electrical field if a unit charge is placed. So effect of that electrostatic force is explained by electrical field like a gravitational field. Okay, this is nothing but the charged particle can be defined to have electrical field around if you place a unit charge around it. So if there is one charge Q, if I place a one unit charge Q, the electrostatic force experiencing by this Q with Q1 is nothing but the electrical field of the Q1. Right. So this electrical field can be given as K into Q1 by R cube into R bar. So the units for this electrical field is volt per meter. Volt per meter. Next, magnetic field. The same like electrical field, we have to discuss about magnetic field. So if a charge experiencing a force moving in a space but does not experience it when at rest, then the region in the space is said to be have magnetic field. Suppose a charge is there Q, if it is moving, it is experiencing some force. Okay, if the velocity is 0, it is not experiencing any force, F is equal to 0. Then we can say this charge is under magnetic field. Okay, this having magnetic field. So the magnetic field is denoted by the symbol for magnetic field is B. And if a charge Q moving with some velocity V, charge Q moving with velocity V, experiencing a force perpendicular to the direction of V bar and B. The magnetic, okay, so this is the velocity direction of a charged particle. Q is moving in this direction and the magnetic field may be like this, though, right. Next, the force that is developing by the while the charge is moving along the in the one direction, the force will be perpendicular to the both V and B. So this will be the electromagnetic force. So the force is electromagnetic force, that is equal to Q V bar cross P bar. It is perpendicular to the both magnetic field and also the velocity direction. Okay, the units for this magnetic force, electromagnetic force, is given as Tesla. Right. So next we will discuss electrothermal thrusters. Electrothermal thrusters. There are two types of electrothermal thrusters. One is a resistor jet, another is a arc jet. Arc jet thruster and resistor jet. So electrothermal thruster, right? there are different types of thrusters: electrothermal thruster, electrostatic thrusters, electromagnetic thrusters. Okay, in that electrothermal thruster. So thermal thruster, we are using electrothermal thruster. We are using electricity to increase the temperature of the gases and produce the thrust. So electrothermal, we are using electricity to increase the temperature of the gases. We expand the gases and the thrust will be developed. Here you can see this is a resistor jet. In the resistor jet, you can see here the small holes like this. So these are nothing but it is a cross sectional diagram. You can see the resistor wires. Resistor wires placed around this tube. Okay. So when you send the charge, when you send the current through this resistor, is a nothing but electrical heater, right? When you send a current through the electrical resistance, it will heat, right? It will generate heat. So when the propellant is flowing through this resistance chamber, the propellant temperature will increase. So the pressure also increases and the propellant starts expanding and moving with some velocity while leaving the nozzle. So it will generate m dot into Vj, which is nothing but the thrust. So this is the concept of resistor jet. We use a resistance to heat the propellant to generate the thrust. Next type of electrothermal thrust is arc jet. Here the arc jet is we developed a electrical arc. So if you take this is a cathode, okay, positive, and if it is a negative, if I place these two charged two cathode and anode very nearer to each other, there will be some arc will be developed. Electrical arc will be developed at particular distance between them. So this arc generates high temperature. So when I send this propellant, when I send a propellant through this arc, okay, whatever the propellant passes through this arc, that will heat to a high extent and it will generate the thrust. Here in the arc jet, you can see this is the anode. Okay, and the black one you can see this is the cathode. Okay, this anode is placed near to the cathode, but there is some gap, almost some gap is maintained. Because of that, you can see electrical arcs are generating. These are the electrical arcs. The electrons are jumping from one anode to cathode. Okay, because of this, high temperature will be developed here. So the propellant is sending through the propellant feed system through the, and it is passed through the electrical arc. The propellant system is passed through the electrical arc. So here the temperature T1 is less. After moving through the arc, the temperature T2 attained by the propellant is high. So T1 is less than T2. The propellants are heated. So after that, because of the propellant are heated, they will expand, pressure will be increases, and to decrease the pressure, they will move towards the nozzle. To move towards the nozzle where the pressure is low when compared to the pressure in the chamber, and it will gain some kinetic energy, that is velocity, and the propellant which is moving leaving the nozzle will have some mass flow at m dot. So m dot into Vj will give you the thrust. So this is about the arc jet thruster. So here the concept is the propellants are leaving the nozzle with some velocity Vj. The reason is here electrical resistance. So that's why it is called resistor jet. We are using electrical resistance concept to heat the propellant. Here we are using electrical arc concept to heat the propellant. That's why it is called arc jet. That is. So this is about the resistor jet and arc jet, which comes under electrothermal thruster. These are the schematic diagrams. Okay, right? So the propellants are heated to a high temperatures using electrical power, and the hot gases are expanded in a convergent divergent nozzle to provide the thrust. So now we'll discuss clearly about the arc jet engines. So electrical arc discharge is used to heat the propellant. So this electrical arc discharge is used to heat the propellant. Hydrogen, ammonia, nitrogen, these are used as a propellants for electrothermal thrusters. Hydrogen, ammonia and nitrogen, these are used as the propellants in electrothermal thrusters. Coming to the next, these gases are heated to the high temperatures in the electrical arc discharge compared to the resistance heating. When compared to the resistor jet, the temperature attained by the gases in the arc jet is more compared to resistor jet. Next, as the gas temperature increases, the specific impulse increases. The propellant flow rate, the propellant velocity increases based upon the temperature attained by the gases. The overall efficiency and reliability of the thrusters, however, decreases with the use of higher temperature. So we impose a limit on the achievable specific impulse. What happens here, as the temperature increases, the performance of the engine decreases, efficiency of the engine decreases because of high temperatures. What happens is when the high nitrogen is used, okay, nitrogen is sent through the electrical arc, it will get heated if you maintain a proper temperature of T2. But if you go beyond T2, this nitrogen may dissociate it into ions N plus and N minus or N minus. Dissociation of the particles happens, gases happens. When this dissociation happens, the energy will be absorbed. Whatever the heat energy developed, that will be absorbed for this dissociation process, and the complete the final output will affect, the final velocity will decrease. So that's why we have to limit the temperature that is going to be attained by the gases. So for that, we have a limit in specific impulse also. There is a limit on achievable specific impulse in electrothermal thrusters. So these losses are also higher within arc heating, since in the region of arc discharge, ionization and dissociation of the gas take place. When compared to resistor jet, arc jet, the losses are more, because in the arc jet the temperature will be very high. So in this region, the gases may get ionized or dissociation of the gases takes place. So some energy losses happens in the arc jet thrusters. Next, the arc discharge and the ignition of the thrust can be automatically started in the arc jet thrusters by commencing the flow of gases into the discharge chamber. When you send the propellant through this gap, automatically this arc will be generated. But this gap, there is a necessary minimum gap designed. If you maintain that minimum gap, then only arc will be generated. Otherwise, the arc does not generate. So the voltage at which the arc forms is given by Fisen's law. So how much voltage to be maintained at particular gap for a particular propellant is given by Fisen's law. So it states that dependence of the breakdown voltage as a function of the product of arc gap. So arc gap, so this is the distance between the two anode and cathode, and the gas pressure, the pressure at which you are sending the propellant into the arc, the gap between the cathode and anode. These two parameters affects the breakdown voltage, the voltage to be maintained, the voltage difference delta V to be maintained between anode and cathode. So if you maintain delta V based upon the pressure of the gas and arc gap, automatically this arc will be generated. If you do not maintain proper voltage, arc does not generate. So the gas flow initiated, as a gas flow is initiated, when the gas started flowing through the anode and cathode gap, enhanced pressure in the arc gap causes a reduction in the breakdown voltage, and spontaneous arc discharge takes place within the impulse. So automatically this arc will develop because of the high pressure gas is moving between the gap of the cathode and anode, and it will heat the propellant. It will continue as the propellant flow is moving through the arc gap. Even we can use some other techniques to initiate the arc. So there are other configurations of starting the electrical discharge that I have attempted, such as using mechanical starter and also forming an arc at small distance and then stabilizing it for a larger distance. So initially, instead of sending propellant with a high pressure, what we can do is we can maintain a small gap. We can maintain a small gap between this. After that, we can move this anode back so that the gap can be increases and the arc will be destabilized. So initially we decrease the gap between the anode and cathode, arc will be developed. After that, we can increase the gap and we maintain a stabilized arc after, and continuous propellant flow can be sent through the arc gap and process continues. So the highest temperature in the arc jet is the region of the arc core. So here the highest temperature can be observed in the arc core. Coming to the applications, Here this arc jet plasma thrusters we use in the space applications, like ability to generate high temperature without combustion, right? So can simulate high enthalpy flows for hypersonic vehicle research. And air, hydrogen, inert gas are used as a propellant in arc jet thrusters, right? So this is about the electrical arc jet thruster. The specific velocity of the gases, the exit VJ, the exhaust gases velocity is very high when compared to the chemical rockets in the electrical thrusters. Next one is electrostatic thrusters. Electrostatic thrusters. Here you can see the diagram. You can see one ionization grid. This is the ionization grid, and this is the extractor grid. Here this is the extractor grid, and this is the acceleration grid. Grid is nothing but a plate with holes. Number of holes. A grid is nothing but a plate here with a number of holes. Okay, perforated plate. So we'll see how this electrostatic thrusters works. This electrostatic thruster works with the electrostatic field. The concept of electrostatic field. Electrothermal thrusters works based upon the heating of the propellant with the help of electrical arc heating or resistance heating. Electrostatic thrusters works based upon building of electrostatic force between the charged particles. Okay, the propellant is electrically charged. Whatever the propellant we are sending in the chamber, that is electrically charged in an ionization chamber and then accelerated to high velocities using an electrostatic field. So first neutral propellant will be ionized. Propellant is neutral here. Okay, this propellant will get ionized with the help of this ionization grid. When this propellant passes through this ionization grid, it will become ionized. So positive ions. Of these positive ions will be extracted with the extractor grid, and here an accelerator grid which is maintained with a high potential difference. Here V and V2 different potentials voltage will be maintained. Because of this, these ions will be accelerated through this acceleration grid. So it will get some velocity Vj. So finally we will get the thrust. Okay, the thrust F here is Mi by Q into Vj. M is the, here you can see Mi is the current and Q is the charge mass and Vj is the velocity of the exhaust gases. The propellant so we are using is the high atomic mass. We prefer high atomic mass propellants like xenon, which is atomic number 54 and mass is 132. And next we use cesium with atomic number 55 and atomic mass 133. And also mercury, atomic number is 80 and atomic mass is 200. But we don't use mercury because of contamination. It will damage the structures. So that's why we don't use mercury much. We can use cesium and xenon for the electrostatic thrusters. So cesium is readily, coming to the cesium is readily ionized by heated tungsten and has been used for the spacecraft propulsion. However, it is reactive, very reactive. Cesium is easily ionized. You can easily ionize the cesium with the help of tungsten filament. Next, the current trend is using of xenon. Now we are using xenon, which is noble gas having atomic mass near to the cesium. Okay, so initially we are used cesium. Now we are started using xenon. So cesium is 55, xenon is 54. Only one is different. Next, it is also possible to use charged particles of some colloidal substances or dust particles instead of ions, and these could be either positively or negatively charged. So the use of the charged colloidal particles to produce a thrust in an electrostatic field is known as colloidal propulsion. We can place one colloidal substance. When the gas heats this colloidal substance, it will ionize. Okay. So since grids are used for the extraction and acceleration of the ions, this thruster is also known as gridded ion thruster. We can see here this is ionization grid, extraction grid, acceleration grids. We are using grids to ionize, extraction and also accelerating. That's why you can call this electrostatic thruster as gridded ion thruster. Right. So high potential difference is maintained between the extractor and acceleration grid. So here you can see this is the extractor grid and this is the acceleration grid. High potential difference delta V is maintained between extractor grid and acceleration grid to provide necessary acceleration to the charged particle. Whatever the potential difference you maintain, that much velocity will be gained by the ions. This velocity Vj will depends upon the potential difference maintained between extractor grid and acceleration grid. So the ionization of the propellant does in two ways. Okay, this is okay. Delta V, based upon delta V, you can get delta Vj here. Next, ionization. This ionization can be happened in two ways. Okay, one is thermionic emission, another is radio frequency generation. Either we can use the concept of thermionic emission or radio frequency generation to ionize the propellant which is entering into the electrostatic thrusters. The thrust levels of these ion thrusters are generally between 2 to 100 millinewton. 20 to 100 millinewton, not newtons, not even newton, it is 20 to 100 millinewton. Okay, the thrust is very less. So, and the efflux velocity is about 25,000 meters per second. The velocity is Vj, that is getting by ions, the Vj attained by the ions is 25,000 meters per second. Okay, so very high when compared to the other propulsion system. The charged particles such as positive ions while leaving the thruster cause opposite charge to be accumulated in the thruster. Suppose if you take the electrostatic thruster, here one grade, another grade like this. Okay, so here whatever the charged particles, this is the acceleration grid, whatever the charged particles you can see here, these charged particles leave the nozzle like ions. So these ions may damage the structure of the engine. That's why it will also cause of a accumulate like a charge, opposite charge can be accumulated on the structure which will damage the structure. So charged particles such as positive ions while leaving the thruster cause opposite charge to the accumulated in the thruster. So the positive ions escaping the thruster leave behind excess electrons, making the thruster negatively charged. What we do is positive ions are leaving, here you can see the positive ions are leaving the chamber. What we do is we place one neutralization cathode. So this cathode releases electrons. This will release electrons. So these electrons will collide with positive ions and make that positive ions neutral. So the ions leaving the thruster therefore will be neutralized. Here these electrons will go and meet positive ions and make the positive ions neutral, so that there is any space charge effect happens in the vehicle. So this can be done by supplying electrons into the accelerated beam of ions leaving the thruster. The electrons are generated from heated cathode comprising a filament or a plate emitter placed downstream of the accumulator. These electrons are developed with the help of a cathode downstream of the gases. So this is about the electrostatic thrusters. Ionization grid, extractor grid and acceleration grid. These three grids are the main parts of the electrostatic thruster. First ionization process, after that extraction of the ions and accelerating these ions, and next final process is neutralization of the positive ions leaving the chamber. Okay, this is the working of electrostatic thruster. Next, electromagnetic thruster. Here we use the concept of electromagnetic field. We use the concept of electromagnetic field to accelerate the ions to gain high velocities. That's why these thrusters are called electromagnetic thrusters. So Hall effect states that when the current flows in a conductor in the presence of magnetic field perpendicular to the flow of current, the combination of the current and magnetic field generates a voltage perpendicular to the both current and magnetic field. Okay, so this Hall effect is used to generate high velocities. Okay, so here you can see the magnets here. This is one magnet, and here this is another magnet, and this hatched portion is an anode. Okay, this is like a tube. Okay, it is like a tube. Okay, so here propellant is sent into the chamber, in the annular chamber. Okay, so because of this electromagnetic force, the propellant enters in the chamber, will rotate, move like a spirals. and leave the chamber. Okay. Here you can see, here this is the annulus cross section. You can see here there is a thermionic cathode which releases electrons, and these electrons are entering into the annular passage. Here you can see spiraling path of electrons annular towards the anode. Here you have anode, and electrons are releasing from cathode and traveling towards the cathode like a spiral, like moving like this. Okay, in the spiral path. So you can see the positive ions, propellant is sending through the anode, and positive ions are moving like this. Okay, here you can see radial magnetic field is kept. Radial magnetic field is kept so that the ions are accelerating in a spiral path like this. Like this, the ions are moving in the annular passage. Okay, so while these ions, positive ions are moving like this, electrons are sent in opposite direction so that electron with interact with positive ion and makes the ions neutralize, but the velocity will be constant. The ions velocity does not affect, and it will leave the chamber with high velocity and thrust will be generated. So an annular chamber is used, and electrons generated in the cathode are allowed to be attracted by the anode along the length of the annulus. Electrons are imparted and attracted towards the anode. When the electrons travel through the annular towards the anode, they get defleated by the Hall effect along the circumferential direction. These are defleated because of Hall effect, and electrons are moving like this towards the anode. So the electrons therefore proceed in the annular passage in the spiral path towards the anode, right? Next, the propellant gas which we use in the electromagnetic thruster is xenon. It is admitted in the annular chamber from the anode, right? So the propellant is feeding from the anode, right? Next, the spirally moving electrons collide with xenon ionize it efficiently, considering the large values of residence time available from the spiraling electrons for interaction with the xenons. This is a very important. This is the main concept. The spirally moving electrons, whatever the moving electrons in the annular passage, okay, the electrons moving spirally, right, like this. These electrons and propellant is coming like this. Okay, these electrons collide with xenon atoms. Okay, xenon atoms and ionize it to positive, efficiently considering the large values of residence time available from the spiraling electrons for the interaction with xenon, and complete propellant will get ionized here. Next, the Hall effect essentially traps the electrons in the annular passage and uses them effectively to ionize the propellant. So whatever the electrons will ionize the propellant xenon into ions. Next, thrust gets generated with the accelerated neutral plasma. This acceleration of the ions takes place in the neutral plasma, and the drawbacks of space charge limit current observed with the ion thrusters is no longer exist. So whatever the ions leaving the propellant chamber, right? These are the anode. Okay, the propellant is coming like this. So electrons are coming like this, and whatever the gases leaving like this. Okay, these are completely neutral because electrons are sending with the help of cathode here. Electrons are sending here, electrons are sending with the help of cathode, and gases are completely neutralized. Positive ions, electrons mix, and completely neutral plasma coming out of the engine. So there is no chance of space charge limited current observed in the electromagnetic thrusters like ion thrusters. In ion thrusters, we can observe some space charge current, space charge effect, but in electromagnetic thrusters, it is completely avoided. So that is one advantage of electromagnetic thruster compared to the ionic thrusters. Next, the exit velocity of ions. There it is 25,000, right? So it is here it is between 12,000 to 18,000 meters per second. Electrostatic thrusters, it is around 25,000. Here 12,000 to 18,000. The magnetic field is about 0.04 Tesla, and the discharge current is about 4 amperes. Since the electrons do not contribute to the thrust, Okay, the efficiency of the thruster is only 70%. Next, electrons are not contributing to generate the thrust. These are not accelerating outside. These are entering into the annular chamber. So only 70% is the efficiency of the thruster. The Hall effect thruster are also known as stationary plasma thrusters. Even we can call this electromagnetic thrusters as SPT, stationary plasma thruster. So ceramic materials are used for the construction of this annular chamber. Whatever the combustion or ionization chamber accelerating there, that is used in the with the ceramic materials. Those are used with the ceramic materials. Okay, the efflux of the ions from Hall effect thrusters has higher divergence as compared to the gridded ion thruster and results in contamination and heating of the spacecraft surfaces. The efflux of the ions from the Hall effect thrusters has higher divergence. So if the engine is like this, nozzle is like this. So if the gases moves like this, divergence angle is 0. So here the divergence angle is more, alpha is more, here alpha is decreasing, and here it is almost 0. So the divergence, the deviation of the velocity flow of gases along the axis is nothing but the divergence. So this divergence is more in the electromagnetic thruster because the gases are moving in a spiral direction while leaving, it will, after leaving the combustion chamber, the divergence is more in the electromagnetic thrusters. Okay, that's why there is some divergence loss there in the electromagnetic thruster compared to the gridded ion thrusters. Next, comparison. We can go through different electromagnetic thrusters here and also principles and propellants used for different electromagnetic thrusters and also the thrust ranges. So magnetoplasma dynamic thruster, MPD, we can call this as MPD thruster, magnetoplasma dynamic thruster. The principle used is Lorentz force, okay, to accelerate the plasma. The propellants used in MPD thrusters are argon, xenon and hydrogen. The propellant range is around 0.1 to 10 newtons. There in the electrostatic thrusters it is 0.01, very less thrust. Okay, here helicon thrusters, RF antenna generates plasma and magnetic fields accelerated, like argon and xenon are the propellants used for helicon thrusters. The thrust range is millinewtons to newtons. Next, pulsed plasma thrusters. The thrust is generates like a pulse. Used pulsed current to ablate solid propellant and accelerate plasma. Teflon and solid polymers are used as a propellants in the pulsed plasma thruster. This is a solid propellant. Micronewtons, very less, micronewtons to millinewtons. Next, variable specific impulse, magnetoplasma rockets, RF plasma generation with a magnetic nozzle acceleration. We use argon xenon for this variable specific impulse magnetoplasma rockets. Okay, 1 Newton to 10 newtons. So this is about the different types of electromagnetic thrusters, small introduction, and the propellants used and the thrust levels. Coming to the advantages. High specific impulse. Specific impulse is more often 2 to 10 times of the higher than the chemical rockets. Okay, longer operational lifetime. We can use these electromagnetic thrusters or ionic thrusters, electrostatic or electrothermal thrusters for a long duration. The lifetime of this thruster is very high when compared to the chemical rockets due to the minimal erosion and small in designs. Okay, next, variable thrust and efficiency through the power modulation and efficient use of propellant leading to the reduced launch mass. The launch mass also can be reduced, and generally we use these electromagnetic electrostatic thrusters in the space, not in the atmosphere. Next, challenges that are going to be faced is relatively low thrust levels. The thrust generated is very less, so we can use these low thrusters for actuation purpose only. So compared to chemical engines, the thrust level is very less, usually like millinewtons. Next, requires high electrical power sources, so we have to use solar arrays, nuclear resource we have to provide for running of this to run this electromagnetic or electrostatic electric thrusters. Next, electrode erosion happens in some designs like MPD thrusters, limits the lifespan. If electrode erosion happens, it will decrease the lifespan. Next, complex magnetic and plasma control systems. These are the challenges to be faced in electrical thrusters. Next, coming to the applications. So, coming to the applications of these electrical thrusters, we can use electrical thrusters in satellites, station keeping, or orbital rising. We can increase orbit size, and deep space missions like NASA's proposed VASIMR for Mars transit, and attitude control. We can change the position of the orientation of the satellite or spacecraft in different directions, and precision maneuvering spacecrafts, long duration interplanetary motions. For all these applications, we can use electrical thrusters. So, this is about the coming to the summary of today's lecture. We have gone through the introduction of electrical and electromagnetic field. What is electrical field? What is electromagnetic field? How the electrical field generates and magnetic field generates leads to the acceleration of the charged like a propellant. Next, we have gone through the electrothermal arc jet thrusters, and we have discussed electrostatic thrusters, how the grids generates the thrust. And next, we have gone through the electromagnetic thrusters, electrical field and magnetic combination of electrical field and magnetic field, and how the thrusters accelerate the ions and produce thrust in the electromagnetic thrusters are discussed. So, this is about the electrical thrusters and the completion of this lecture series. Thank you.